Welcome back. Section 5 is on units and measurement. We're going to get into the metric system today and how to convert with prefixes, as well as solving some equations with density and volume displacement. It's important in science to have standardized units, so that way scientists can compare results accurately from one part of the globe to another. If everyone's definition of what, say, a meter was different, if it was all different, then it'd be very hard to compare our results. And so in 1960, scientists met to define the terms in the metric system, to give us some standard definitions of what they were. There are 7 base units, okay, of the metric system: time, length, mass, temperature, amount of substance, electric current, and luminous intensity. Ones that we are going to see this year regularly: we're going to see mass a lot, we're going to see temperature a lot, we're going to see amount of substance a lot, which is a mole. The moles will be your best friend by the end of your time in chemistry. We will occasionally see time, we will occasionally see length if we're trying to calculate, say, density and cubic centimeters or something like that. But we have a lot of problems that involve mass later on, a lot of problems that involve temperature later on as well. We may get to electric current this year, but this is more of a physics thing. And then luminous intensity we will not see. You probably won't even see it in a general physics class, candelas. But here are the base units for these. Seconds is the base for time, meters is the base for length, kilograms the base for mass, Kelvin temperature, moles again is the amount of substance. It's like a counting number. Think of it as like a dozen meaning 12. Well, a mole means a specific number, like a dozen means 12. Amps are for electric current, and candelas for luminous intensity. But just because it's not on this list doesn't mean it's not an SI unit. These are just the base unit. You might notice, for instance, that there is some stuff missing, like, say, velocity. Okay, that's not to say that we can't measure velocity. It's just that velocity is measured in metric system in meters per second. It's a combination of distance or length over time. Okay, so we can have derived units, which is what these guys are right here. Okay, but these 7 are independent of everything else, so we had to define what they were specifically. So we're going to figure out exactly how they determined what these units are. Okay, these are the 7 base units. Anything else is a derived unit. It's some kind of a combination of these 7. What happens if we get really large or small numbers when we're using the metric system? Rather than writing out a bunch of zeros, which we already saw is time-consuming and you're more likely to make mistakes, what we've done is we've made prefixes for these units. Okay, and so this chart over here on the right, I would make sure you get this down in your notes or screenshot it, whatever it might be here, but this is going to be very helpful for you to solving problems in this section, and we'll talk about how you use it here in just a moment. But these prefixes are super convenient and super easy to use. The SI system, the System International, is based on powers of 10. Okay, so every one of these is some kind of 10 raised to some power. And after the first couple here, you'll notice it's every 3, since we tend to separate numbers every 3 with a comma. But for instance, if you look at kilo, the value of kilo is 10 to the third, or 1,000. Okay, which means if you have a kilo of something, you have 1,000 of it. Okay, if you have 1 kilometer, that's 1 times 10 to the third meters. Now, there's no base here, okay? This is where the base unit would be. So if you only see 1 letter, like these 3 examples here, okay, that's your base. It doesn't have to be M. It could be liters, it could be seconds, it could be whatever. But if you don't have a prefix letter, okay, like this K here, if you just have just a single letter, you're in the base units. But it's really easy to use because whatever you have here in terms of kilometers, it's just 1,000 times that in meters, 1 times 10 to the third that, okay? Let's say you had 2 kilometers. Well, it's 2 times 10 to the third meters. If you had 2.1 kilometers, it's 2.1 times 10 to the third meters. So really all we're doing here is just using times 10 to some exponent, okay? We're more or less getting things written in scientific notation, which is, again, why we learned that. It makes this easier to do the math. Here's the chart again. It's a little bit bigger for you if you want a better picture of it. But we're going to make reference to it and use it to solve some problems going forward. So make sure you've got this down. Okay, so we're going to start down here on the bottom of how do we actually do these conversions when it gets a little bit more complicated. I'm going to walk through the first one as part of this example. I'll do the second one with you, and then I want you to do the third and the fourth ones on your own and see how you do. Okay. So this problem is wanting us to convert 1 liter into some number of deciliters. Okay. So how do we do this? Well, the first thing you would do, right, is you would just write out your original value. So our original value here is 1 liter. Okay, so we just write that out. The second thing we need to do is find the difference in the exponents of both units. Okay, it should say of both prefixes. All right, we'll go ahead and change that here. So it should say of both prefixes. Go ahead and make sure that's clear for us. And I would definitely make sure you've got these rules written down as well. Okay. So, both prefixes. So this one, since it's just a single letter, that's my base unit. There are not 2 letters here, so this is just a base. Okay, that's 10 to the 0. All right, I just copied this from the previous chart, okay, on the previous page. And then deci, lowercase d, is 10 to the negative first. So how far apart are they? Find the difference in them. Well, 0 and -1, how far apart are they? They're 1 unit apart. Okay, it doesn't have to necessarily be positive or negative here because it actually matters which direction you're converting from a bigger unit to a smaller unit or a smaller unit to a bigger unit as to whether it's going to be positive or negative. For now, you just want to know how far apart are they. Okay, so this is 0 and -1, so they're 1 unit apart. And then the third step, if you're converting from a larger prefix to a smaller prefix, exponent is positive. If you're converting from a smaller prefix to a larger prefix, exponent is negative. Okay, so here, all right, this is base unit, right? Okay, and this is deci. This is a larger unit compared to deci. This prefix is higher up than deci. So I'm going from a larger to smaller. Okay, larger to smaller. Larger to smaller, meaning my exponent's going to be positive. Okay, so all I do is just multiply by that value then. 1 liter times, and it's 10 to the first deciliters per liter. All we're doing is multiplying times that 10. Now this is to the positive 1, because we're going from larger to smaller, and I get 10 deciliters, okay? All right, so let's look at the second example. Here I'm going to go from kilometers to millimeters, all right? So my first step was to just write down the original value for kilometers, so I wrote that down. Step 2, find the difference in the exponents of both prefixes. So we need to go find kilo. Kilo is 10 to the third, okay? And we're going to millimeters, all right, so lowercase m here, and that is 10 to the negative third, all right? So those are 6 units apart, okay? So it's either 10 to the 6 or 10 to the negative 6, depending on which way we're going. So we know it's either plus 6 or minus 6. If we're converting from a larger prefix to a smaller prefix, the exponent is positive. Well, I'm going from kilo, which is a bigger unit, to a smaller unit. So it is going to be positive. It's going to be positive 6. So this is going to be times 10 to the 6th. Okay, and you can write as an answer 4 times 10 to the 6th millimeters, or if you want, you could write the whole thing out. 1, 2, 3, 4, 5, 6 millimeters. So you're talking 4 million millimeters is the same as 4 kilometers. Okay. I want you to try these two on your own here. By the way, this one right here, that kind of odd-looking U is the Greek letter mu. Okay, is what it actually is. And that stands for micro. So this is micro liters is what that particular unit is. Micro is 10 to the negative 6th. Okay, so when you see that micro, it's the Greek letter mu is what that is. So I want you to try the third and fourth one here on your own and see how you do. Okay, now that we've got the prefixes covered, let's talk about what the base units actually are. Okay, so time. If you think about it, how do you stop and define time? How do you set what is exactly 1 second? So in a way that it doesn't change. So what scientists did is they've based it off of an atom. They based it off of cesium-133. Okay, so time is defined as a very specific thing. This cesium atom, all right, I'm just going to draw some crude drawing of an atom here, not actually what an atom looks like, but you get the point, okay? What it does is even atoms in a solid, okay, things that aren't, movable like liquids or gases, even atoms in a solid vibrate along all of their axes, okay, and I'll just draw this one going like back into the screen there, okay? It moves back and forth. It vibrates on all axes, so it can kind of move back and forth in all directions here. And they counted exactly how many times this thing vibrates, and they said, we'll set a certain number to be what 1 second is. And if we sit here and put some commas into this number, we realize just how large it is, right? Thousands, millions, billions. So this atom, the cesium-133 atom, vibrates 9 billion something times. And when it hits this specific number, that's what 1 second is, okay? So this doesn't change. That's why they picked this, because it's consistent, that no matter what, even if something else changes in relativity with space and time, we can still count how many times this thing vibrates and define that as 1 second. So that's how they defined what time is. It's kind of cool. They used an atom and talked about how much it's vibrating, and how many times it vibrates in a particular set amount of time is what 1 second is. So that's what time became. 2 more units here, mass and temperature. So how do we define what a standard for mass is? Well, mass is the measure of the amount of matter an object contains, right? You often think of this as like how much something weighs, okay? But it's really a measure of how much matter is in this object, okay? What it's based on these platinum and iridium cylinders. And if you pay attention and look at your periodic table, platinum and iridium are kind of in the middle there. You got PL, and then you've got iridium, which is IR. These are considered part of the noble metals, meaning that they don't react, okay? Most metals, if you leave them exposed to the atmosphere, will eventually oxidize, okay? Iron's famous for that. It turns, iron into rust. Copper will turn kind of a light green color. Most metals, when you leave them exposed to the environment, will eventually rust. Well, platinum and iridium don't rust, okay? So they made these cylinders out of platinum and iridium because then they know they're not going to gain mass, because they're not going to oxidize. They're not going to rust, okay? Then on top of that, so they take this cylinder and they put it inside of a glass container, and then they suck all the air out of it, making that a vacuum. And then if that weren't enough, just to make sure that it doesn't change mass, they do it again. They put another container around that and suck all the air out of that. So this thing is completely isolated. There's no air in here. There are no gas particles in here that could react with this cylinder, meaning its mass is going to stay the same. And that's what a standard kilogram is, okay? And notice, it is in kilograms, not grams, is the standard, okay? So this weighs, kilogram is about 2.2 pounds, just for reference, all right? Roughly speaking here, okay? But that's how we have the standard for mass. It's based off these cylinders, okay? Temperature is really the measurement of average kinetic energy of particles that make up an object, okay? So temperature, like the temperature of the room you're in, what you are experiencing is the average kinetic energy of those particles. How fast are they moving? All right, so let's say you've got some kind of a container here, or a room, or whatever. Here are gas particles. Some are moving faster than others, okay? The temperature you are experiencing is the average of all this motion, okay? The temperature of the objects coming out of the oven, all right, is an average of the motion of those particles. In general, as motion increases, temperature increases. So if we speed these things up, or if we heat up this room, these particles start moving faster, or the room heats up, okay? If motion increases, temperature increases, and the opposite's true. If you cool stuff down, the particles slow down. There are 3 units of measurement here: Fahrenheit, Celsius, and Kelvin. We are pretty much never going to use Fahrenheit for anything. There's times where we may use Celsius, but most of our actual calculations later on in the year are going to involve Kelvin, which we'll talk about. So as Americans, we're used to the Fahrenheit scale for temperature. While it's helpful because at least like roughly 100 degrees we know is hot, and 32 is when ice forms or melts depending on which direction we're going. It's really kind of a useless scale. Basically, a guy created his own thermometer, right, and then just arbitrarily put lines on it and then figured out at what point does water freeze and what point does water boil, just based on these arbitrary lines he drew on a thermometer, which it isn't actually very meaningful. It was helpful in the sense that it at least gave us a scale to work with. So this was in the 1700s, but it didn't really have an exact value for us to work with. So it's all arbitrary. Later on, guy Celsius, he's going to say, okay, instead of 32 and 212, what if we set water freezing to 0 and water boiling at 100? Because then we have some points to work with, some consistency. And here's the conversion for that. If you're going from Celsius to Fahrenheit, it's this equation. If you're going from Fahrenheit to Celsius, it is this equation. Okay, so we've got both of them here. I would make sure you've got these equations down for how to convert those temperatures. Now, this is still helpful, but the problem is we can have negative temperature, right? Negative temps in Celsius. We can have negative temps in Fahrenheit as well. But this is not good. If you're trying to plug stuff into an equation, think about it. We just said that temperature is motion, right? It's how fast something is moving, okay? To have negative temperature, how do you define that, right? Are you saying it's going backwards? Well, but going backwards is still moving. So we can't have this negative temperature in calculations. It doesn't really work like that. So another guy, Lord Kelvin, took the Celsius scale and figured out at what point is actually 0, or what point is 0 motion, because 0 motion should correspond to 0 on the temperature scale, right? If I just have an object and it's motionless, okay, it's just sitting there, then this should be at 0, whatever that is, because temperature is motion. So he calls this, well, we call it now the Kelvin scale. He'd say that that would be at 0 Kelvin, motionless atom, okay, or object or whatever, okay, 0 Kelvin. It's not moving. And so he figured out what that 0 point was and then related it to the Celsius scale. He says water freezes at 273 Kelvin and boils at 373 Kelvin. Notice, do not say, put this in quotes, degrees Kelvin. Not correct, okay? Because degrees is saying that there's some sort of a scale here. This is an absolute scale, not some sort of arbitrary scale, because there is a 0 point and there is no negative temperature. So Kelvin we call the absolute temperature. 0 Kelvin means there's no kinetic motion. Kinetics meaning moving. There's nothing moving around. Okay. So the conversion then from Celsius into Kelvin is we take Celsius and add 273. All right. We should have no negative temps in Kelvin, okay? So that's why that scale was invented. Later on, when we're talking about gas laws, we're going to use Kelvin because we can't have negative temperatures in those equations. Okay, so those are all the base units that we might see this year. Let's talk about derived units for a second. So if you go back to the original 7 base units on the chart, okay, there were some units that you know exist that aren't on there. I gave you one example was velocity, okay, which we said was meters over seconds. Another example here is going to be volume, which we'll talk about. So these are called derived units. So not everything is just from a base unit. We use the base units to create derived units. So an example here is volume. All right. Volume is really distance in 3D. Okay, we saw earlier that the distance is a base unit. Okay. All right, and it's measured in meters. Okay. So volume is just distance in 3 dimensions. Right. We're thinking length times width times height is volume of a regular shaped prism. Okay. The volume is the space occupied by an object. So measuring length, width, and height of cubic or rectangular objects. The SI unit is meters cubed, which it's easy to visualize what that means. So if you take a meter stick, and by the way, 1 meter is approximately 39 inches, roughly or so. So imagine a box, right, that's a little over 3 feet tall, 3 feet long, and 3 feet deep, okay? That would be what the base unit for volume is in the metric system. The problem is most of the objects that we're going to be measuring this year in chemistry and most of the objects that you look at in physics aren't going to be large enough to need this, okay? Unless you're trying to like measure the volume of Earth, okay? Then you'd have a lot of these. But most of the stuff that we're doing is going to be considerably smaller than a 3 foot by 3 foot by 3 foot box, all right? if we have a regular solid, so something that's not, nice and easy shape, something that doesn't have an equation to calculate volume, we measure that using water displacement, okay? And the test for Unit 1 will have a water displacement problem, and the last problem, or the last page on this set of notes will have a water displacement practice problem for you. Okay, so as I was saying a minute ago, cubic meters is usually too big, so we often use liters. A liter is a cubic decimeter, or we'll often see is we'll use milliliters. A milliliter is a cubic centimeter, so imagine what a centimeter is, right? It's probably roughly about that long in real life. Okay, I don't know how big your screen is that you're looking at, but something along those lines, right? Okay, so that's what a milliliter would be if you could imagine that in 3 dimensions. All right, probably roughly about that size. This is more along the lines of what we're going to be using, not this 3 foot by 3 foot by 3 foot cube here. Okay, so this is another practice with prefixes. We can use the prefixes with the base units. We can use the prefixes with derived units. Go ahead and try this one. Go back and look at the rules of how to do this. Okay, find the difference between your prefixes. Are you going from bigger to smaller or smaller to bigger? Okay, and make that conversion. So go ahead and try this one on your own and see how you do. Okay, last couple slides here. We're going to take a trip back to density. Which is mass over volume. Hopefully you've got this equation down. You might also see this, you might see density on an equation sheet in the future written as what looks like this. This is the Greek letter rho. Okay, Greek letter rho. Okay, RHO. It kind of looks like a P and a J combined. So if you see what something looks like rho equals m over v, then it's just density equals mass over volume. Okay, you might see it as d equals m over v. Either way, no matter how you want to write it, if you see it written in variables, you might see this. If you see it written in words, it'll look like that. Just don't get worried about this. That's a Greek letter rho, meaning density as well. Okay, the units here are usually grams per cubic centimeter or grams per milliliter. That's because mass is measured in grams and volume is either cubic centimeters or milliliters, right? And since this one's on the top and one of these two is on the bottom, this is the unit that we would come up with. Okay. The cool thing about density is that it's specific to each element. So every element on the periodic table has a specific density, and if we can calculate it, then we can identify what that element is. So let's say you have a sample of something and you don't know what the density, or if you can find the density but you don't know what it is, you can go look it up on a table because those values are out there. Okay, so if we can find a way to calculate density, we can figure out what element we have. Okay, this last example here is an example of a water displacement problem. There's going to be one of these on the first unit test, and there's going to be one of these on the first semester final. So an example like this. This is an important problem to understand. Okay. So the problem says when a piece of aluminum is placed in a 25 milliliter graduated cylinder that contains 10.5 milliliters of water, the level rises to 13.5 milliliters. Given that the density of the aluminum is 2.7 grams per milliliter, what is the mass of the aluminum? Okay, so we do this for irregular solids, okay? Things that don't have an equation to describe it, right? We're not talking about length times width times height here, okay? Because this object, all right, we're saying this piece of aluminum is not like a regular prism. So what's happening? You're taking this piece of aluminum, you're putting it in a graduated cylinder. Graduating meaning it's got the lines over here, the cylinder for the shape, and it's filled with water, okay? It's initially filled with 10.5 milliliters. After that, all right, once you've put it in there, now notice our piece of aluminum is down here on the bottom now. We are up to 13.5 milliliters. All right, so we'll say that my initial volume, VI, is 10.5, and my final volume is 13.5. Question is, right, first, before we even plug stuff into the density equation, what is the volume of the aluminum, right? What's the volume of the aluminum, which we'll abbreviate with its atomic symbol Al, okay? Well, to do that, volume, we'll say, of aluminum, Al, in this problem, is the final volume minus the initial volume. This volume here minus this volume should tell us how much this thing is taking up, okay? So mathematically, final volume is 13.5 milliliters minus 10.5 milliliters. The volume of the aluminum is going to be, don't forget significant figures now, right? Because your calculator would just say 13.5 minus 10.5, but we go, since it's subtraction, the one that goes the least far to the right is as far to the right as we go in the answer. They both go to the 10th place. My answer better go to the 10th place. So make sure it's 3.0 is what you would write for the volume of the aluminum. Now it says, we know the density of it. What's the mass? Okay, so my equation, density is mass over volume, rho equals m over v. The one thing I don't know is mass, so I'm just going to use algebra and bring the volume up to this side. Just rearrange it, multiply both sides by v. I get density times volume is equal to the mass. And if we plug those values in, the density is 2.7 grams per milliliter, and the volume is 3.0 milliliters. Okay, 2.7, do this on my calculator, times 3.0, and I will have, now it's a multiplication and division problem. I've got two significant figures here, two significant figures here, so my answer better have two significant figures. Comes up with 8.1 grams. Okay, and the grams is coming from, grams is coming from that G right there. Okay, so then my milliliters would cancel as a unit, leaving me with grams. So the answer here would be 8.1 grams. Okay, you will have a problem like this on the first test and on the first semester final. So make sure we understand what's going on here. We're putting this irregular shaped object into the graduated cylinder. The volume is going to increase. To find the volume of that solid, we subtract the final volume minus the initial volume. Okay, that gives us the volume of the solid, and then we plug that into the density equation to figure out either the density or the mass, whatever it might be. Okay, that's how we could figure that out.